You might have been wondering why AI can create things that never existed. And this is exactly why this particular video is important. So, why AI can create things that never existed? It is basically because of generative distributions and the mathematics of creativity. And we have its applications in multimodal AI. When we talk about multimodal AI, we're talking about things like generating text, generating voice, generating image, and things like that, generating videos. So learning objectives, by the end of this lesson, you'll be able to understand what generative AI really learns, distinguish between discriminative and generative models, explain probability distributions mathematically, and understand generative distributions. Learn how AI samples from probability distribution and explore latent representations. Understand multimodal AI mathematically and implement simple generative models in Python. Then we appreciate why AI can generate entirely new content. That's why you can tell AI to generate a flying lion, which is not realistic in real life, but then it can put the ideas together. So, by way of introduction, one of the most astonishing abilities of modern artificial intelligence is its capacity to create things that have never existed before. Examples include human faces that belong to nobody, paintings by imaginary artists, new melodies, original poems, scientific hypotheses, computer programs, videos from text, 3D objects, virtual worlds. So these outputs are not copies, actually. Instead, AI learns the probability distribution of real-world data and then samples new points from that distribution. So it's more like AI has different tools together. It's more like you're given all the ingredients, and then, for instance, as a Nigerian, we know we have jollof rice, we have fried rice, we have white rice and stew and everything. But then you are given all the ingredients for making all of these things. So you can end up having maybe fried rice and stew or whatever you want to come up with, so you have all the ingredients, you can then put them together in whatever way to get something totally new that was never known to the particular culture those ingredients are from. So that's why the outputs are not copies. Instead, AI learns the probability distribution of real-world data and then samples new points from that distribution. This mathematical idea is called generative modeling. So the entire field of generative AI, including ChatGPT, DAL-E, Stable Diffusion, Gemini, Claude, Sora, and many others, is built on this single principle of generative modeling. So this lesson explains the mathematics behind that remarkable ability. So the central idea is this, that generative AI does not memorize anything. It doesn't understand your language. It doesn't understand images. In fact, all it understands is the vectors, the probability distributions, and vector embeddings that those things represent. And then it can permutate and and combine these things in such a way that it can form new ideas. So generative AI does not memorize. Instead, it learns what kinds of objects are likely to exist. So it has a wide array of possible objects that can exist, and then it can pattern after them. Mathematically, instead of storing examples, it estimates probability of X, where X represents data, images, text, audio, video, molecules, or even code. This probability distribution contains all the statistical patterns of the data set. Once AI learns this distribution, it can generate completely new samples. So we talk about probability distribution. A probability distribution tells us how likely different observations are. For discrete variables, P of X equals X, for instance. So for continuous variables, we have P of X. So these are just, we're talking about the mathematics behind artificial intelligence. So the mathematics behind artificial intelligence are the normal mathematics you have always known, right? Like probability distribution, like that you have here now. And we just have it in the context of AI. So a probability distribution tells us how likely different observations are. For discrete variables, probability of X equals X. For continuous variables, you have probability of X with the probability is summation of probability of X dx equals 1. That's for continuous variable. But for discrete, now summation of all X is equal to 1. So a distribution assigns probability mass or density to every possible observations. So mass goes with discrete and density goes with continuous. So generative AI attempts to estimate this unknown distribution from data. That's what generative AI simply does. Example, imagine a data set containing 1 million cat images. Each image is one point in an unimaginably large image space. So the AI never stores this exact cat. Instead, it learns eye shapes, fur patterns, whiskers, hair geometry, lighting, poses, and even colors. So collectively, this can define probability of cat images now. So if you now tell AI to generate a cat image, it will just sample this whole probability distribution and put together possible features, and then you can find some kind of cat. So for instance, I can just say, um, I need a a a horse-looking cat. Makes no sense, right? So I need a horse-looking cat, right? Generate, generate a horse-looking cat. So here we're talking about a cat, right? Then I also mentioned horse. So it's going to sample the probability distributions for cats and horses and put together features from both horse and cat and then give us something that is going to be interesting. So I'll go and come back to see what it would have given us. So because it would have led distribution for horses and cats, and then it can sample all this and put together a horse looking cat. So it's still the work is still on. So on this, once distribution is learned, new cats can be sampled even though they never existed. So horse-looking cats don't exist, but all right. So you can see this is a horse right now, but it's looking this is a cat, but it's looking like a horse. So those are the kind of things. Okay, I can just say make. I don't know if a red cat ever exists. Make a red proper cat now. A red proper cat. Okay, so so you can just let your ideas run wild because all the ingredients are there. So AI just puts it together based on your request or based on what it feels should be the result, right? So let's talk about two types of learning as I go watch. Okay, this should be ready pretty soon. Okay. Let's see. So there are two types of learning when it comes to image generation, right? We have discriminative models. So that's probability of Y given X. Examples. This is good for image classification, spam detection, diseases diagnosis. So it is so this as the name implies. Now, okay, now we have a proper cat now that is red. So this looks more like a cat as compared to that cat that was looking like a horse, like that. So the major thing it picks from the horse there is the head and the hair on the neck and the tail too. But here we have a proper cat right here. So what about if I say make it a blue? I'm trying to look for a weird cat kind of. So let's say blue cat, right? Make a blue cat. So I'll come back to check. So we can have discriminative models, right? Which are good for image classification. So there are from the word discriminative, it tells you that this here you want to remove anything that is not part of it. So it's more like you're going straight for the image, not anything that does not look like it. The question a discriminative model answers is this. It is like, what is this? So I'm looking for a horse. Does this really look like a horse? That is what that is answering. Then we have generative models, which is our concern here. So generative models learns probability of X. So while discriminative models learns probability that of Y given X. So what is probability that it is a horse given what I have right here? And then it can tell it apart now. Or so for that part of image disease diagnosis now. So maybe there's a particular skin disease now. Given what I have here, what is the probability that this condition is this particular skin issue? Okay, this is still in the works. So here now, you learn probability of X or probability X comma Y. And the question this answer is what could exist. So this one is giving you what is possible to exist, not just what exists. So generative models create new observations. Examples include ChatGPT, Stable Diffusion, GANs. That's generative adversarial networks, then VAEs, variational autoencoders, and then you have diffusion models. This can give you possible things that might exist or things that can exist based on what the model already knows. Then we talk about generative distribution. Suppose X1, X2 up to Xn are training examples. So these are images upon which the model is trained. They are assumed to come from some unknown distribution, say P sub data of X. Then the objective is to learn P theta of X, where theta are model parameters. So it wants to learn for the data available now. So given these parameters, like I'm talking about a horse looking cat, you know, so it has to pick features from both cat and horse to get that. So here I said I wanted a blue cat, so now we have blue cat. It's even asking me which one I really prefer. So I think I prefer image two because it's the bluer the better, because I was asking for a blue cat. So this is our blue cat right here. Now we have training. Training minimizes the difference, right? So theta are model parameters. So this training minimizes the difference between p sub theta of x and p sub data of x. P sub data of x is the original data upon which the model is trained. Then p sub theta of x is extracting whatever you have prompted the AI to do. So based on the parameters you have given it, like in the case of the horse looking cat now. So I'm saying, okay, it should be a cat, but it should be looking like a horse, like that. So what if I ask for a bird looking cat? Bird looking cat. So in the original, ChatGPT has been trained with tons of images of birds and cats, but then the parameters I've set should be things related to cat and bird together. Let's see how that comes out later. So now the question is, once p sub theta of x is very close to p sub data of x, that is what you're looking for is close to what exists. So new samples are generated by drawing this distribution that x is distributed according to p sub theta of x. So the learning distribution, then the model parameters are chosen to maximize the loss as a function of the parameter values, which is the product of all possibilities from I equals 1 to n of p sub theta of xi. Then if we take the logarithm sound, then the log of L of theta is the summation from I equals 1 to n of log p sub theta of x are x sub I, and training minimizes minus log L of theta, called the negative log likelihood. So nearly every modern generative model optimizes some variation of this object, like that. So uh so here we are talking about image generation, even for text generation, right? What we are trying to, as much as possible, to get as close as possible to what is expected. Okay, now imagine this is really funny. So you have a cat with wings, because I asked for a bird looking cat, like that. So I mean, in essence it's cat, but then we can see the body has like what's the body of a bird, so to speak, you know. So nearly every modern generative model optimizes some variation of this objective. So here now we have you know, we do random seeding to ensure that we always get the same result. So we can have samples from a learned distribution. So this is generated from random values, right? So what this seeding is doing here is to ensure that no matter how many times we run this code, we always get the same distribution. So you see that the distribution is always the same because of that line 4 here. But if you don't care about the distribution that comes out each time, then line 4 doesn't matter anymore. So imagine if I silence line 4 by using a hash. So each time I run this now, you're going to get a different distribution. So you can see this one is getting up to 0.4 now. So if I do it again, okay, still 0.4, but you can see the shape currently always changing. So the shape is always changing. Shape always changing. So you can see the shape keeps changing like that because I removed the seeding now. I've allowed it to be random. So if I let me run it once more and then put the seed in place. So now it's like this. So I can, if I remove this now, it can then remain the same permanently. So now no matter how many times I run it, it will always be the same because of that line 4. So if you are working with random values and you don't want them to keep changing, so you have to do np.random.seed and put a number in brackets. Usually I'm used to seeing 0 and 42 in brackets. So sampling now, after learning the probability distribution, AI generates data by sampling X, which is distributed according to p sub theta of X. So every sample is different. This explains why every prompt can produce a unique output. So every sampling is random. So you can have a unique output. Even when the same model is used, you can always have a unique output. So if I ask for a red cat from AI several times, I'm still going to get this. I'm going to get different. I mean, I demonstrated that with one red card the other time in one of the earlier videos. So example, suppose X is normally distributed with mean 50 and variance 10 squared, that's 100. Find the probability that x lies between 40 and 60. That is, the x lies between 40 and 60. So the solution, the first thing we standardize, we get a z-score, which is x minus mu over the standard deviation. Yeah, over the standard deviation, yeah, over the variance, yeah, this variance here. So for 40, we know that to be 40 minus 50, which is minus 10 divided by standard deviation. Standard deviation will be square root of variance. This is variance, right? So standard deviation is square root of that. So we have variance. That'll be 10 over minus 10 over 10, which is minus 1. For 60, that's 60 minus 50, that's 10 all over 10. That is 1 again. Therefore, we know that z lies between minus 1 and 1. And if you take the probability of that, that's like 0.6827, and that's approximately 68.27% of generated values. So it means 68.27% of generated values lie within one standard deviation, like that. So we can easily do that here using SciPy or stats. I did a playlist on scientific computation, and part of the things we saw there is SciPy, that's scientific Python, which involves a statistical library module. Yeah, so we can get num from there. So here we have probability, uh cumulative distribution of 1 minus uh cumulative distribution of minus 1. So taking the norm of that, that's how to get this now from minus 1 to 1. So we go up to 1 and we subtract minus 1 from it, because the idea is we have a build up to 1, then we remove everything up to 1 from that idea. So and we get the 0.6827 approximately, like that here. So that's what this gives us. Then we have latent space, which a whole video was dedicated to previously. So you want to check that out. That's the inside the beautiful space or something like that, where uh, image generation dwells or something like that for image models. So latent space, instead of generating images directly, many AI models first generate a hidden vector z called the latent variable. Typically, z is normally distributed with mean 0 and variance 1, because it is matrix, that's unit vector. Unit vector represents 1 in matrix. So a decoder then transforms z to x. This converts simple Gaussian noise into images, music, speech, molecules, or even text. So then we have variational auto encoders. So variational auto encoders learn encoder Q of Z given X, and then so the encoder, this is the noise being added now. So Q of Z given X, and then the coder now P of X given Z. So a given a noisy image encoder, yeah, given a clear image, how much noise? What given a noisy image, how do you get the original image? And then the coder says, given the image, how much? I mean, it can be a reversal of both, right? Given a given a clean image, how much? How given a clean image, how much noise should you get, or something like that? And then given a noisy image, how can you get retrieve? That's probability of retrieving the actual image given the noisy one. There was uh probability of getting the of noise given the original image, something like that. So training maximizes the evidence lower bound, ELBO. So here, L is now the expectation of log P of X given Z minus D sub KL of Q of Z given X, then together with P of Z, like that. So this balances reconstruction accuracy, and you have smooth latent distributions, allowing interpolation and generation. And then we talk about diffusion models. Diffusion models gradually destroy images by adding Gaussian noise. So you have x sub t equals square root of 1 minus beta sub t, then x sub t minus 1 plus square root of beta sub t epsilon, where epsilon is normally distributed with mean 0 and variance 1, or I in matrix form, identity matrix. So the neural network learns to reverse this process, recovering realistic images from pure noise. So this is why random noise eventually becomes a coherent image. So random noise over time becomes a coherent image at the end of the day. Now we have generative adversarial networks, and as the name implies, it's adversary, right? There's an there's a there's a there's some there's a pull something pulling it up and something else is dragging it down. So there's that adversarial thing. So GANs contain two neural networks. You have the generator, which creates fake samples, and then you have a discriminator, which tries to distinguish real versus fake, right? So by creating the fake samples and this, by the generator creating fake samples and the discriminator trying to distinguish the real one, the optimization object, we can get the image at the end of the day. So the objective of that is the main minimization. We minimize the effect of the generator and maximize the effect of the discriminator for V of D comma G. That's discriminator and generator equals the expected value of the log of the discriminator of as a function of x plus the expected value of log of 1 minus the discriminator as a function of the generator of z. So this adversarial game drives the generator toward realistic outputs. So they are back and forth. As the generator is generating samples, the discriminator is trying to shave off anything that is not needed, and then at the end of it, over time, the proper image is obtained. So we then have why AI create novel objects. I mean, that is has been made clear already. So, but to drive the point home, the generated output usually never appeared in the training data, right? Instead, the model combines learned statistical relationships. For example, an image generator may combine one person's eyes, another person's hairstyle, another lighting condition, another background, another camera angle into an entirely original image. The output is statistically plausible and not memorized. For instance, I've been taking a lot of examples. Say how to generates the picture of a Japanese looking Nigerian, Japanese looking Nigerian. So it has learned the possibilities, right, of what are the what do Nigerians look like? What do Japanese people look like? So in essence, this person is a Nigerian, but then the person should be looking like a Japanese person. So that's basically the concept. So everything that it has learned, it's more like just the best example I've given is that you have all the ingredients to make, say, jollof rice or and fried rice and white rice, and then you just put the recipes together in a particular way, and you come up with your own unique your own unique kind of food in that case. So that's the idea here. That's why AI can generate new ideas. So an image generator may combine one person's eyes, another person's hairstyle, another lighting condition, another background, another camera angle into an entirely original image. The output is statistically plausible and not memorized. So it's not like it's been memorized beforehand. No, it's just so it can just permutate and combine stuff to get new ideas out like that. So I hope the Nigerian looking Japanese person is ready now. Oh, okay, this is not. Nippon, no, no, you're not Nigeria. Okay, Nippon, no, you're not Nigeria. Interesting. That's Japanese looking Nigeria. Did I say Nigeria or Nigerian? Well, it doesn't seem to capture the person. So in that case, oh, I said Japan looking Nigeria. No, should be Japanese looking Nigerian. So now I didn't signify whether it's a man or woman. So maybe I should say Japanese looking Nigerian man. Yeah, Japanese looking Nigerian man. Let's put it that way. So, as we wait for that, applications of generative distributions now. Generative distributions power many modern technologies like AI art, image generation, video generation, speech synthesis, music composition, drug discovery, protein design, game content generation, robotic simulation, data augmentation, scientific discovery, and personalized education. Then we have 40.12 multimodal AI. So, multimodal AI talks about the different forms like text, images, speech, and all that. Humans naturally integrate multiple forms of information. We have text, we have images, we have speech, we have videos, and we have gestures. Modern AI aims to do the same. Multimodal AI learns a joint generative distribution, say probability of getting a particular text, and image, and audio, and video. That's why you can have a video with text and of course with the images and also audio, sound, and visuals. So you have everything together, text, image, audio, video. But of course, going by social media behaviors, videos seem to make more impact than, say, uh, audio, or maybe audios will make more impact than images, and images more impact than texts, like that. Aha, so this is a Nigerian man that is wearing kimono like that. So make the facials, Make the facials Japanese. So I even want the face to look like Japanese. I don't know how that's going to be, but let's see. But I think we can see a possibility in maybe children who are born by a child born by a Nigerian and a Japanese. So you can have all the hybrid thing going on there. Okay. Because these modalities share statistical relationships, the model can generate an image from text, then it can describe an image with text, then it can answer questions about videos, it can create speech from text, it can generate videos from written prompts, it can combine audio, text, and images into a single coherent response instead of learning separate worlds. Multimodal AI learns one unified probabilistic representation across different data types. So one thing I've not been using a lot is videos. I've not been doing videos a lot. So maybe after this one, I'm going to generate the image of a Nigerian speaking Japanese. Let's see how that goes. Now, let's go to 40.13, joint and conditional distributions. Suppose T is text, I is image, A is audio, and V is video. That is TIAV. So a multimodal model lens probability of TIAV. From this joint distribution, we can derive conditional distribution such as text to image. That's probability you have an image given a text. So that's text to image. Image captioning, probability of text given an image. So you have an image, then you want to get a text from that. Then you have speech synthesis. That's probability of getting an audio given a text. So with a text prompt, I want to get an audio. Then visual questioning answering. That's probability of getting a text given an image and a question. So where Q represents a question, right? So these conditional distributions allow the same model to perform many different tasks by conditioning on the available inputs. And that is why you can upload a picture. Now, see, this is the best it can come up with a Nigerian looking a Nigerian man with a Japanese face. That's really hard to conceive, but it's fine. Uh, Nihon to Nigeria. That is, you can see this here. Nigeria and Japan and Nigeria. That's what this means. Nihon to Nigeria, like that. All right. So, let's say Japan generates the video of a Nigerian man speaking Japanese, like that. Okay, so then we can have this code now. So okay, this like what we did the other time. So nothing too special from. So it's more like demonstration of sampling. So you can have all kinds of sampling there, but because of the seeding here, the sample remains the same. If you remove the seeding, that automatically changes, like what I demonstrated before. So this is up to 100. Now check what's going to happen. Now that I remove it, now it can go to 80 at some point. At some other point, it comes to 100 again. Then you see the shape is shifting 80 again. Then so the shape keeps shifting like that, and you keep having different shapes for this. So, but of course, if we allow the seeding to work, we have one fixed shape that does not ever change. So with this now, it doesn't change anymore because we have put seed in there. So if you want reproducibility, don't forget this crucial line, np.random.seed. Then in summary, in this lesson, we learned that generative AI models learn probability distributions rather than memorizing examples. So yeah, let me see. Oh, okay, this is difficult. I can help create the concept scripts and shot by shot for a video of a Nigerian man speaking Japanese, but I can't directly generate. Okay, I mean that's like that's not so straightforward, but it's okay. Let's just keep going. So in this lesson, we learned that generative AI models learn probability distributions rather than memorizing. Now, I think ChatGPT has that video capability, yeah, except that I've not. Yeah, can we see? Is it? Let's see now. Let's see. Is it new chat? Maybe not new chat library. Okay, I think under new chat we can still get that, right? New chat here, and then I want. Okay, yeah. Okay, yeah. Let's just keep going. So in this lesson, we learned that generative AI models learn probability distribution rather than memorizing examples. And the goal is to approximate the unknown data distribution, P sub data of X, with a model distribution, P sub theta of X. So new context is generated by sampling from the learned distribution. So don't forget the ingredients analogy. You have all the ingredients and you can come up with your own unique recipe. So you're given all the ingredients for a particular kind of recipe, and but then you can combine yours in in another way that that is unique. So that's why AI can generate new things. So new content is created by sampling from the learned distribution. So maximum likelihood estimation is a fundamental training principle here. So latent variables provide compact representations for generation. Variational autoencoders, generative adversarial networks, and diffusion models implement different strategies for generative modeling. So multimodal AI learns joint probability distributions across text, images, audio, and video. So you can give a text and get images. You can give an image and get text. Maybe just say, "Oh, tell me about this image," and you get text. You can put a text and get audio. You can put an audio and get text. You can put text to get video, and you can put video and get and answer questions about it or something. You can put an audio and get video, whatever. So, and that enables flexible cross-modal generation. So you can switch between the text, image, audio, and video like that as you like it. So modern generative AI systems can create realistic original content because they model the statistical structure of data rather than copying it. So they don't memorize anything per se. So here we have our practice problems, very straight to the point, 20 of them. So the first says define the generative distribution, and the 10 says explain the reverse process in diffusion models. Of course, the reverse process is the process of denoising to get back with the image that that must have been started with. So yeah, so let's go ahead and talk about so here I'll be solving problem 7 and 15. 7 says derive the log likelihood from the likelihood function. So we're going to deal with that. It's a very straightforward derivation. So derive the log likelihood from the log likelihood function. Then the other, I'll be solving 7 and 15. So 7, that's 7. So we can say all of 11 to 20 here. So I'll be dealing with 15 again. Derive the conditional distribution for probability I of t from probability t, comma I, like that. So yeah, so we go on and deal with that right away. So problem 7. So for problem 7 now, given the likelihood function L of theta, which is the products across I equals 1 to n, and we have p sub theta of x sub I. So if we take the logarithm, right? So we're talking about log likelihood. So taking logarithm yields, so straightforward, we just have the log of L of theta equals summation from I equals 1 to n of log of p sub theta of x sub I. So we take the log like that. Of course, we know log helps us a lot to make sure things don't overshoot their boundaries. So that's one use for log. So we have that. So this log now, so this which converts, so logs convert a product into a sum, making making optimization, making optimization numerically stable, numerically stable, and computationally efficient, and computationally efficient. One idea we've encountered in the process of this whole journey of the mathematics of artificial intelligence is that, so because we deal with tons of data, it's possible we get very large values that makes learning unstable. So, and we've seen part of what we do to mitigate that is we can do scaling, as we see scaling in the case of attention equation, and then in this case now, in the case of loss, we can take uh, of likelihood, right? We can take logarithm also to balance to make sure that we don't have things overshooting like that. Okay, so let's go ahead and talk about problem 15. Problem 15. So we need to, if you remember question 15, right? We need to get probability of T from probability of T comma I or something like that. So, and we just go like this, starting from the definition, starting from the definition of conditional probability, of conditional probability. So we have probability of image given text. So what's the probability that you're going to get an image if you're given text? That will probability of text and image all over probability of text. So that's conditional probability. Probability of image given text is probability text and image all over probability of text. And what does that simply tell us? So where probability of T is equal to summation over the whole image, then the probability of T comma I. So that's like some marginal kind of probability now. So when you have the probability of text and image together, but we are focused on image, so that gives probability of text. So that's for discrete variables, or of T, probability of T equals integral of P T comma I, integrated over I like that. So that's some kind of marginal probability that we come across under the concept of probability. Now, what does that teach us? Okay, this is so that's for continuous variables, right? For continuous variables. So what does that teach us then? Um, okay, this conditional distribution, this conditional distribution is the mathematical foundation, is the mathematical foundation of text to image generation. So the model generates an image conditioned conditioned on the supplied text prompt. Supplied text prompt. So it's more like generate an image given the text prompt you have. So with that, we come to the end of this interesting video talking about why AI can generate new things altogether. So it's been such a nice experience so far. And you've seen the idea of generative distribution. So again, look at the 20 questions. We have 1 to 10 right here, the practice problems. 1 to 10 right here. I did 7. So I was able to derive the log likelihood from the likelihood function. So it's just about taking the log of both sides. Then I did 15, deriving the conditional distribution, probability that we get an image given a text from probability of both text and image together. So let me know how helpful this is for you. And if there's something else you'd like in trials, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, this is a good time to go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges as you click, gives you some special privileges as a member of the channel as you click on join. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.